So we introduced this idea of kinetics and the rate. So let's actually talk about how to actually calculate rates. Again, the rate changes with time, and so we're usually going to be talking about the average rate at a certain moment within the system. And the way we do that is we look at the change in the concentration as a function of time. So it's the difference in the time and the difference in the rate. So the rate of reaction is how much compound is consumed during a particular time interval. And so in our bromine case, it's how much bromine is changing. And so we talk about this delta concentration, in this case bromine, delta T. And again, where delta is always, the final minus the initial. So that's what our delta means. So whatever the final is. And so we can look, and for the record, this small t, minuscule t for time. All we need to do is, find what the initial bromine is, bromine final, or minus bromine at some time 0, or whatever the initial time is. So you'll see a lot of subscripts here. These subscripts are to denote when. And then our time final minus time initial. Right? So this is a particular easy way to do it. Right? And that would give us the average of the bromine being consumed during that time interval. This is a hydrocarbon being broken down into other hydrocarbons. So let's look at what the rate is between, say, minute 100 and minute 150. Okay, so we're going to take so we're going to look at 150 or so. So we see that the molarity at the initial time, final time of 200, 0.00596 molar, minus the molarity at 0.0071 molar, and this is minute final minus initial, 200 minus 150, so this will give us 50 seconds, and then the difference between these concentrations would be negative 0.00114 molar. And if we simplify this, divide those two numbers, 2.28 times 10 to the minus 4th molar per second. Negative. Negative 2.28. Now, this may seem like an odd number, negative, but we're talking about the disappearance of the bromine. Starts high, ends low, and so it's disappearing, it's being consumed. Right? So this is a weird convention, the negative sign. Right? Oftentimes we'll eliminate that. We'll talk about that in a second. So the rate is, it's going down, minus 2.28 molar every second at this particular juncture. Now if you take a look at the rate at one of the other times, say between 200 and 250, you'll see that it is not 2.28. Right? So those, if you take a look between 200 and 250, you'll find, prove this to yourself, that the molarity, the rate is at 200, the average rate is 1.92 times 10 to the negative 4th molar per second. Right? Well, which is the rate? Well, again, it's the rate is used specific to a moment within the reaction. Right? The rate starts high and slowly decreases in time. This is exactly what we see. At time 200, between 200 and 250, the average rate is 1.92 times 10 to the minus fourth negative bromine per second. Okay. And so that can be a little bit odd, like thinking about this in terms of the negative sign. We are going to eliminate that, though. Almost always rates are reported as positive values. And we'll talk about why in a second. But at this moment, the rate that it is disappearing, negative. Again, you can talk about it as like the actual concentration value. You can play games with the language where you say, what is the rate at which it's disappearing? Well, then it would be 2.28 times 10 to the minus fourth molar per second. It's disappearing that fast. It's like how much my paycheck is disappearing. So rates are almost always reported as a positive value. Again, notice rates start high and then slowly decrease. Right? The concentration consumed over a unit of time slowly decrease. And this is a very normal phenomenon for reactions. So a little bit different. What if we looked, instead of at the starting material being consumed, what if we looked at the amount of the C2H4 showing up? Right? Between the same amount of time, you can see that where this goes down a small amount, this goes up by a much larger amount. Small amount, larger amount. So you can talk about the gap between those spots. Well, it turns out that that's really not that odd if you look at the stoichiometry. For every one of these that's consumed, you make two of these. So the C2H4 is appearing twice as fast as the C4H8 is disappearing. Right? So the rate of increase between this point and this point is going to be twice the rate of decrease this point to this point. You can actually prove that by looking at the calculations. You could actually pick two convenient points. Oh, we'll say this 0.5 unit here. Okay, this point's at 0.12-ish and drops down to 0.05, so that's 7 units, whereas this one goes up by almost 14 in the same time speed. All right? So, this one drops down by 0.07 units, this one increases by 0.014. Now again, that's the stoichiometry during the same time. So looking at different things, each of them has a different rate, but the rates are tied together. And so the way we solve this is that when we express the overall rate of a reaction, the overall rate is irrespective of stoichiometry. You take the rate that you calculate and you divide it by the stoichiometric coefficient with a negative sign if you're using a starting material, or the coefficient with a positive sign if you're using the reactants. Again, the negative sign is just there as a side effect of how we're looking at the reaction, final minus initial, when you're dealing with a starting material. Again, we typically do not express a rate as a negative number. It is how fast the reaction is going. Doesn't matter if it's increasing or decreasing. So the apparent rate, the rate with respect to one of the components, say B, will be different than the rate with respect to the other component. But the overall rate of the reaction will be the same. All of these rates are tied together by the relationship. If one of them has a stoichiometry of 2, it will increase twice as fast. At 3, it would increase 3 times as fast. And so we eliminate that. We just talk about the overall rate of the reaction. All right. So let's look at this description, how we discuss the rate. At a particular time, the reaction is found to be consuming nitrogen oxide being consumed at 0.0130 molar per second. All right. So how fast the NO2 is being consumed. 0.00130 molar per second. That's how fast that material is going away. Right? So technically it's a negative 0.0013. Okay? So how fast is the molecular oxygen being consumed? Right? Well, if this was 0.0013 molar per second, that's how many molar of the NO2, the oxygen would be consumed 1/4 as much. And so as the amount of NO2 decreases, for every 4 of these, it consumes 1 of these. So if these are at 0.130 molar per second, this will be about 0.004 molars per second, 0.0004 mole, 4 times 10 to the minus third molar per second. Okay. And what rate is the nitrogen dioxide being produced? Well, it'd be twice, half that, so 0.65. So for every 4 of these, you make 2 of those. The overall rate of the reaction would be whatever this was divided by 4, because with respect to nitrogen dioxide. If you do the calculation for each of these, you'll see that they all produce the same exact rate of consumption overall for the reaction. Okay, so that's about how we measure the rate. In the lab, one of the reactions we would have looked at iodine. We would have measured the starting point, how much iodine was in solution. We'd hit the stopwatch and start the reaction, and then we'd watch until the iodine color disappeared, and then we'd take an instantaneous rate, change in the iodine concentration as a function of time. That would represent the rate of that reaction with respect to iodine. And then we correct that for the overall stoichiometry. That's what we normally do. We measure, and then we just report this value. In general, we just report the rate. In practice, the way we do that is we measure a concentration as a function of time. So, overall tips for dealing with kinetics. Keep these in mind, all right? When you look at reactions, you want to compare what exactly are you given, all right? So, for instance, if you're looking at rates and time, that's a very different set of problems than rates and temperature. And then rates and stoichiometry, all right? So those all those relationships are all tied together. We try to get around the temperature thing by holding everything constant, and the stoichiometry plays a role in what we're looking at, but not like it does in equilibrium. And lastly, there's this idea of a rate law and a rate constant. The rate of a reaction is controlled by an experimentally derived equation called the rate law. And the rate law has a general form, but it's not fixed for a given set of chemical reactions. For one reaction, it always has the same rate law, and it has a constant associated with it. And so part of our game with this is determining those constants. And we'll talk about the rate laws in the next unit. All right? Take-home message. The rate of a reaction is independent of stoichiometry, even though the NO2 may be decreasing 4 times as fast as the O2, the overall rate of the reaction will be the same, and you can prove that to yourself. If this was 1.03, you can figure out that this was 1/4 as much, and this would be twice as much as the O2. And you can prove that to yourself, and I highly recommend that you do. Rates are likely to be largest at the start of a chemical reaction. So if you look at the change in the concentration as a function of time, the change here between these two units is substantially more than the change here, even though the time unit is the same. Concentration versus time relation. That's because reactions slow down. The fastest part of a reaction is right. And then the units. Okay? Oftentimes we're going to be dealing with units of concentration and time. And so if you're dealing with seconds, things will be written in seconds. But hours and minutes and days are all reasonable for time units. Typically, though, we just talk about concentration. Though occasionally they will substitute in partial pressure.